I'm also a machine learning. I'm also a machine learning engineer here with Dana, and today I'll be covering data wrangling. So let me go ahead and share my screen. Is my screen visible?
Yes, we see it.
Perfect. Thank you. So yeah, let's get started. So I already have this notebook run. And also, please feel free to interrupt me at any time if you have any questions or anything you'd like to add. I might not see your messages, so you can just unmute yourself and ask. So yeah, we'll try to be as brief as possible. This lesson is split into two parts. The first part, we generally discuss data wrangling techniques, the most common ones anyway. And then in the second part, we'll go through an actual cargo project and just see the areas where those data wrangling techniques discussed are applied. So yeah, let's get started. So yeah, so what is data wrangling? According to Wikipedia, it is referred to as the process of transforming and mapping data from one raw form into another format, with the intent of making it more appropriate and valuable for a variety of purposes. In a nutshell, it's just the process of converting your data from one form into another, depending on the use case. So yeah, so the first data wrangling technique we'll be looking at is tidy data. So typically data is said to, oh yeah, sorry, I can share this link so you can follow along with the notebook, and you can run it as well, and you can also see. Messages. Sorry about that. The Zoom was interrupting with my. Just going to share that again. I apologize for this. Just bear with me one moment. Can anyone else open the Colab link, or is it just me?
I have
Okay,
to open it in a
perfect.
private window.
Okay.
There we go.
Okay, that's fine. So yeah, so let's get started. So yeah, so we're looking at so our data can either be in a long versus wide form. Let's look at that. So the long form typically referred to as this is what is referred to as the tidy data form. In this form, each variable forms a column and contains values. Each observation is a row, and each type of observational unit forms a table. Okay, so let's look at this as an example of the wide format. This data was taken from the UNICEF website. That's the link where it's taken from directly. As you can see, the data is wide. Each column refers to a year, and while each row refers to the country. This could be converted using the pandas melt function, and that can be made into a long format. So here, each country is still an observation, and the years now form entries in the rows as well. And we now have the values in one column, where before they were in each and every column. There are many advantages to using it this way. Some libraries, for example, some different visualization libraries expect different kinds of formats. Now, it is also possible to convert from long to wide. Here, we can use the pivot function to do that. So let's go a bit more into detail into how this works. So in the melt function, we feed in the variable name that we wish to remain constant. In this case, that is the country, right? So we wish for the country column to stay the same, but everything else we are converting from wide to long. So the first argument passed in is the country name. Then we pass in the name that we wish to name the column, where all the previous columns are now being arranged into. So that is date. As we can see, the name of the column here is now date. We also provide in the name of the column where the values are going to be in, which in this case is M rate, which stands for mortality rate. So now everything is arranged in this form. Now, while converting from long to wide, we again pass in the name of the column that we wish to remain constant, which again is the country name. Now, bear in mind, we can pass in more than one name. We can pass in multiple columns as the columns that we wish to remain constant. Now, this time we pass in the name of the column that we wish to convert from long to wide, which again is date. And then we pass in the name of the column where the values are present, which is the M rate, which is the mortality rate. As we can see, the data is now back to, so can you mute your mic if you're not currently speaking? Thank you. So yeah, so as we can see, the pivot function allows us to convert the data back from the long format to the wide format. So let's move on. So the next thing we'll be looking at is reshaping our data in the forms of merging, concatenating, and to compare. So here we have, now if you're familiar with SQL, you might already be familiar with some of these. Yeah, so if you're already familiar with SQL, you might be familiar with some of these join types. We have the inner join, the outer join, the left and right join. Now, this visualization sort of explains how this works. So the inner join matches, so let's show an example. Columns, the L key and the value, the right key and the value. If we were to perform a left merge here, we perform that using the merge function. We call it on the first data frame, the one that we wish to be on the left. Then we pass in as the first argument the second data frame. We pass in how we wish to join, which is a left join, as well as the key that we wish to join it on. So this is the key where we are checking for matches. So when we join these two data frames, we're saying match based on these two columns, on this column for the first data frame, and on this column for the right data frame. And we're asking it to join them wherever there are matches here. So in this case, they have the exact same value, which should not be. So let's try something else. Oh no, I'm also as well. Let's just make this. Okay, so we perform a merge. Okay, so now because we're performing a left merge, what that does is it looks at the data frame on the left. It checks for matching keys with the data frame on the right. We have a match with foo. We have a match with, we don't have a match here. So with foo, so what we're left with is foo twice and bar and this FO. So yeah, so what happens is all the keys on the left are kept as is. What is this? Am I the only one seeing this? Oh, that's the annotate.
No, you're not.
Let's clear that. Oh, okay. I don't think it's from my side. I think, Madhu, can you look into that? So just click on the annotate and click clear. That should remove that, clear all drawings. Okay. Let's close that. Okay, so what the left merge does is it keeps all the keys in the left data frame constant, and then it checks on the right for the keys that match. So there we have this. So we have foo, bar, and fo because these exist in the first data frame. Then where we have foo matching on the right as well, it matches that. And we get the 5, 7, 5, and 8 because these are the only two entries that match the first one. Now let's move on to the right merge. Right merge is exactly like the left, except now it looks at the data frame on the right and then it merges based on those. I'm sorry, please, if anyone's not asking any questions, could you mute yourself, please? Thank you. Okay, so the right merge does exactly what the left does, except this time it looks at the data frame on the right and then it merges based on that. So in this case, we have, let's run this again as well.
Hi, Sage.
So on the right side,
It's the left merge.
Sure thing. So for the merge, we're merging the DF1 and DF2, right? Now we've specified that we wish to merge based on these keys, based on these columns. So for the left data frame, we are merging based on the L key, which is this column. And for the right data frame, we're merging on R key, which is this column. So what the merge does is, what the left merge does is, it keeps the data frame on the left constant. It keeps all the entries on the left data frame. Then it adds the entries that match on the right key. So in the left key, we have foo, bar, and fo. Those are kept, foo, bar, and fo. Those are kept constant. Now, the only matching key on the right side is the foo, right? That is the only one. These are the only ones that match keys on the left side. So that is why it carries over 5 and 8 onto this side. For bar and fo, they don't have matching keys here. So those are nans are placed in there because there is no matching entry from DF2 to carry over to the merge. Is that okay?
Yes. Thank you.
Sure. So
there's a question in chat, if I may read it.
Right. Sure. Sure.
Oh, I think you're breaking up.
You have multiple instances. Hello? Hello? Can you hear me?
Oh
Yeah,
yeah, I
we can
hear it
hear
now.
you.
Oh, perfect. So someone's asking what happens. Oh yeah, so just to let you all know, I don't necessarily see the chats when they come up because I'm sharing my screen. So please just unmute your mic and just ask. You're asking what happens when you have multiple instances under a single key on the right. So we do have that actually. Oh yeah, you mean on the right, let's see. So yeah, we have that. We have foo twice and it's copied over twice. So here we have foo twice. Because of that, we have two foos. One, that's why we have one entry, which is a 5, the other is an 8. We have that here as well. Notice that foo only exists once in the first data frame, but in the merged data frame, we have foo twice. That is because we have two foo twice in the right data frame. Okay, so the right merge does exactly the same, except this time it looks at the data frame on the right. That is the one that is kept constant and used for the merge. So in this case, again, we have foo twice. And then, so this is a nan left key. So these are nans, but this is a baz. So the reason for this is because baz exists in the right table, that is kept, but there is no matching key on the left because there is no baz here. So that is why these are replaced with nans. The inner merge is very different from the first two we discussed. So what an inner merge does is it doesn't look at the data frame on the left or right. It simply only keeps entries where there is a match, on both sides. So in this case, the only entry that has matches on both sides is foo, and that is why foo is written multiple times. So for each entry, for each of the observations, it sees that there is a foo, it carries that over. There is a match here, which is 1 and 5, 1 and 8. But the second foo also matches with the first foo. So that's why there's also another, so yeah, so we have 1 and 5, 1 and 8. That comes from, so the first foo, 1, matches 5 and matches 8. So 1 and 5, 1 and 8, and then we have 5, 5, 5, 8. So that is this. So yeah, so this matches the 5 and 5, 8. Sorry, I need to see that. Full, left and right, left and right.
I think you should rerun the cell. It will solve the
Oh,
problem.
okay. So yeah, because I changed it, right? You're right. Thank you. Thanks for that. Oh yeah, this makes a lot more sense. So yeah, so we have the 1 and 5, 1 and 8, which is just a match, as we see. So 1 and 5, 1 and 8. Okay, so now we have an outer merge. So an outer merge is sort of like the opposite of the inner merge. It keeps everything. It keeps everything in both data frames and just keeps a nan in the places that don't match. So here we have the exact, the full data frame, full bar full bars full. Everything is kept. And in the places where they don't match, they're just replaced with nans. Now, all of these different types of merges, they all have different use cases. And it always comes down to you merging two data frames for a specific purpose, which we'll come to, because we actually look at an example where we merge together two data frames much later. So that's it, we merge, we come to concatenate. A concatenate is somewhat different from merges because with this, we're not matching based on keys. We're just adding together two data frames. These can be merged in one of two ways. They can either be stacked on top of one another, or be placed side by side. So here we have examples. So these are two example data frames, data frame 1 and 2. They both have the exact same features. Both have 3 rows, labeled 1, 2, 3, 1, 2, 3 for simplicity. So in the first case, we start them using the pandas concat method. We feed in a list of the two data frames and we specify over what axis is we wish to, well, sorry, not merge, we wish to concatenate them. So we're concatenating over axis 0, which is a row concatenate. So here we see the two of them combine. This is the first data frame, and this is the second data frame. So see that 1, 2, 3, 4, 5, 6. I should like everything. Let's check that again. This is odd.
I think that's because of the head method.
I'm sorry?
I think because the head method is there, that's why.
Oh yeah, it's showing the first 5. You're right. You're right. It's only showing the first 5. We can display everything by specifying 6. Okay. So 1, 2, 3, 4, 5, 6. Yeah, thanks for that. So we can also concatenate across the column, across columns. So this is where we stack them side by side. So this here, 1, 2, 3 is the first data frame. 4, 5, 6 is the second data frame.
Are we done with
So
that?
now we've increased,
Application
in this case.
Me too, but I didn't see any message.
Okay. So yeah, so in this case, because we were stacking them by row, we kept the same number of columns, but now we have more rows. In this case, we are keeping the rows, but now we have more columns because we are stacking the 2 data frames side by side. So now we have 4 columns as opposed to 2 that we had before. We'll just go through the compare real quickly. So compare just compares 2 data frames. You feed in 2 data frame, and it tells you how they differ from each other. So this is the DF1, that's the self. It has entries 1, 2, 3, but the other, which is the second data frame, has 4, 5, 6. And for the second column, so we have the self and the other as well. Now, I know that sometimes it might be difficult to really picture where these might be important. So that is why the second half of the lesson actually goes through an actual scenario where they're being used. Okay, so now we have changing the data layout. We'll be looking at sort. We are able to sort the values. We're able to sort the entries in a data frame by, sorry, someone speaking. Do you have a question? Okay, so we're able to sort the values of a data frame. In this case, we have this data frame, which we, so this is the child mortality data frame, the long data frame that we created earlier. Let's just print the data frame again to see what it looks like normally. So what it looks like normally is that it was sorted by country, right? So by country alphabetically, with Afghanistan, Albania. Here we can sort it by the same country column, country name column, but tell it like feeding the parameter ascending false, so that they are sorted in a descending manner. So here we have Zimbabwe being first, and all the Afghanistan entries are now last. We can also sort the mortality rate, which is this. Now the highest mortality rate now at the top, and the nans are under. For different reasons, we might want to rename our columns. So here we're renaming the columns country name. Yeah, sorry, please, if you're not asking a question, can you please mute your mic? Thank you. Thank you. So yeah, so we're also able to rename the column names. So in this case, we could say that, oh, that rather than maybe say country name, let's have it named as country. And instead of M rates, which is not very clear, we can have it named as mortality rate. So it's now clearer what the column means. So this is the new data frame with mortality rates and country. We might also want to drop specific columns from a data frame. Now, why might we want to do that? So before we just add this, so we add this date column, right, with this USMR before the year. This is a string. However, we might want to use the date, the year as a number, right? We might want to check the difference between the date and the present time, 2021. We might want to create a new column that represents 2021 minus this date. But we would not be able to do that in this present format. So to do that, we can subset the last 4 values, which would be this, and then convert it to integer. So that now leaves us with this. So we have this new year column that is now that now more accurately represents the year variable. Then since we have this, we no longer need this dates column, right? So we can drop that using the drop function. In this function, you can specify multiple columns if you wish to drop multiple columns. We also specify the axis because we are dropping a column that's an axis of 1, whereas rows will be 0. So this is the new data frame with the year column and the date column gone. Let's move next to subsetting values in a data frame. Again, this is the long CME data frame. We can view the first 2 by passing in the head. We can specify how many entries we wish to see. Here we are seeing 2. If we don't specify a value, as we found out earlier, it only shows, by default, it shows the first 5 rows, the first 5 observations. However, we can specify how many entries do we wish to view. We can also use the tail, which looks at the last entries as opposed to the first few entries. We can drop duplicates. So certain machine learning algorithms don't perform well when you have duplicate entries. So it's always good to check this and make sure you don't have duplicate observations. So drop duplicates does that automatically. It checks across all rows and it looks for other rows that have the exact same values and drops them. We can subset rows by index. So if we use the index LOC, passing it the values of 5 to 10 to give us the 5th to the 10th entry, not inclusive. So 10 is not inclusive. We can subset data frames by single columns. So here we can subset the rows by values in a particular column. So here we are subsetting rows that where the year equals 1950. So this returns a new data frame where it's only showing us all the entries that are 1950. Sorry, does anyone want to ask a question? Yeah, I'm sorry that I keep saying this, but when you make sounds, I assume you want to ask a question, and that sort of that is a bit of a distraction. So can you please keep muted when you're not asking a question? Thank you. Okay, so we can also subset by multiple conditions, also by columns. So here we are asking our data frame to give us entries where the country name is Afghanistan and the year is 1950. There is only one entry that matches both of these conditions. We can also ask our data frame to return a sample. So here we're asking for a sample of 100. by using the sample function and specifying n equals 100. So how does this differ from head? Head simply picks out the first n values. So the first 5 or the first, however, but a sample takes them randomly. So that is why there is no, that is why these indexes are not sequential. And also there is no, there's no logic to, like there is no, the country names are not sorted alphabetically. It just samples them randomly. We can also use the frac parameter, which tells it the waking up of the data. We're asking for 0.1, so we're asking for 10% of the data. These are also sampled randomly. Okay, so we're done with rows. Now we can look at columns. So here we can ask specifically for the country name column. So this gives us the different country names. We can also ask for multiple columns. Here we are subsetting by using the two square brackets and passing in a list of the columns that we want. So here we could ask for 2 columns instead of 3, and it should give us country name and year. We can also ask for a column range. So we can say take everything from country name to year. In this case, this is inclusive. It picks up the year as well. We have that. We can also ask for country name to end rate, and it gives us 2 columns. Okay, so another way to subset by columns is to use indexes. So here we can ask it for the first column to 3. This is not inclusive. So this gives us column 0, 1, and 2. Here for this is for the rows. So here we're asking for all of the rows. This column signifies everything. So rather than this, for example, we could say 0 to 5, and this gives us the first 5 rows, but it gives us the first 3 columns. So as we saw here, we can subset with both columns and rows. So using the LOC, so the main difference, so this we're using ILOC, this stands for index. So this is when what you're passing in is an index, like numbers. So you're saying 0 to 5, 0 to 3, 0, 1, 2. This is indexing using a number index. But LOC, using 0 and 1, we are passing in actual values. Like here, we're using column names to signify that we want country name and mortality rate. And here we are saying that we wish for it to subset by this condition for the rows. So we are asking for rows where the year is greater than 1950. So this returns to us country name and mortality rate, because those are the only 2 columns we ask for. And we have rows that match this condition. So let me just check if there are any questions. Okay. Okay, so so that's it with the basic data wrangling techniques. So I picked this out of Kaggle. This is also very, very short. Now, because this is not a modeling or data accuracy workshop, this is a data wrangling. So the focus is mostly on the data wrangling to get the data ready for modeling. The project we'll be looking at is the Rossmann store sales. This is the link to that. You can check it out. So the idea is, so Rossmann is a store in some European countries. The problem was about building a predictive model that could predict for a given day what the sales would be for that store. So I downloaded the data in advance and stored it here. So for easy, this is just to make it easy. After some days, this will expire. So if it doesn't work anymore, you can just download the data from Cargo yourself, and you should be able to just do everything else the same. So for now, we'll be importing, so there are four data sets in this computation. So there's the, so there's the train, test, the store CSV, and the sample submission. So this is just a quick description of the dimensions of the data. So we have about 1 million records, so it's a lot of data. I'm sorry, could you mute your microphone, please, if you don't have any questions? Thank you. Okay, so for now, we'll import 3 data frames: the train, the store, and the test. We'll import the sample submission later on when we wish to see what the submission should be like. Sorry, can you share this? Yeah, thanks, Jabir. Okay. So so we have over 1 million entries for the training set. There are about 1,115 stores, and we have about 41,000 entries for the test set. This is what the training set looks like. It contains the store, the day of week, the date, the sales made on that particular day, the amount of customers that came into the store, whether or not the shop was open, whether they have a promotion ongoing, and whether there's a state holiday and whether there's a school holiday. In the store data sets, we have a few more features. So including the type of store, whether there's competition and the distance, when the competition was last open, the year, the month and year it was open. This is a different promotion column, which I believe is best to just open up. You should be able to look at this as well. So someone was just asking the source of the data. It's on Cargo, so just search for Rossman. Okay, so we have a few more features from store. So naturally, we would need to merge the train and the store data frames to get all of these extra information for each of the observations in train. Now, because train is the main data set that we wish to learn from, and store is just giving us additional information, this should be a left merge where we are keeping train constant and we're just merging with store, and we're just adding all the extra information that comes with store. So we do that here again with the merge. We specify train is the left, is the data frame on the left. So we call the merge on that. We pass in store because it's the data frame on the right. This is a left merge. We specify that here, and we're matching it on the store column. So both of them have store columns. Now, if both of them did not have the same column name, we could specify left on, right on. However, we don't need that because they both have a store column. So this is what it looks like after the merge. So this is the training data set. Now it has all the information from the store data frame added to it. So yeah, let's do some general checks. Just see, we like to see if there are any null values present in the data. Pandas data frames have a is null function that just sort of checks, and then we sum them so we can see how many. The reason why these are summed is because if we just run this by itself, it returns a data frame with just true and false values where there is none. So this is false because there is no null here. This is false, but wherever we have true, that means a null is present. So to get something more meaningful, we just sum them. And that just gives us, for each of the columns, how many null values are present. For most of them, there are no null values present, but for these last 5 or 7, So these has a lot of null values. I mean, out of a million observations, we have about 508,000 nulls. So that's a lot. Okay. There's the .info function that just lets us view some general information about the columns. This also tells us how many null values are present. So in this case, or rather how many non-null values are present. So again, we see these they don't have null, but with these are the non-null. But this also lets us know the type of the columns. So store is an int. This is a categorical column, so object. A few of them. Now, so in the process of in pre-processing our data and wrangling, these are the things that we need to take note of, because naturally, a lot of machine learning algorithms require numbers, right? They're performing mathematical calculations. So we would need to find some way to convert those categorical values into numeric. So now we notice date is an object. That's because it's the date written as a string. We notice the state holiday and store type, assortment, and promo interval. These are all non-numeric. So the first one we'll be looking at is the date. So with this, we can just convert it to a date time format. So with the date time format, it is now, let's print an example of this to see that. So by running there's the pandas dot, see. Oh yeah, sorry. I forgot I had already run everything before. So yeah, everything has already been run and date had already been removed later on. So to see that, we can just run this again. So we have the date, it is now in a datetime format. If we view the info again, we'll see that date is now a datetime object. Okay. So there are also many important features that could be extracted from the date, from the date feature. We could get out the specific day, the month, the year, the day of the year. So this counts from 1 to 365. We can get the week number and whether or not it's a weekend. So these ones are pretty straightforward to get because the date time as an inbuilt where it just gives us the day and month and everything. But here for whether or not it's a weekend. So we have this day of week that goes from 1 to 7, right? 1 to 5 being Monday to Friday, and 6 and 7 being Saturday and Sunday. So we can use the apply method to just simply ask whether or not the value is greater than 5. So this is referring to 6 and 7. So if it's a 6 and 7, rather than returning a Boolean, which is true or false, converts that into an integer. True is converted to 1, false is converted to 0. So now we have an extra column that tells us whether or not it's a weekend. We can also use the describe method to get some other general information about the numeric features. So this gives us the count, the mean, standard deviation, the minimum value, the 25th, 50th, and 75th percentiles, as well as the max value. This can be quite informative because we can use it to get an idea of our features. For store, we have between 1 and 1115, which makes sense because we know we have over 1,000 stores. and they are just numbered from between 1 and 1,115. The day of the week goes from 1 to 7, which makes sense because they are numbered 1 to 7. For sales, we have 0 sales. And then we have up to 41,000 euros, I'm guessing, as the max sale in a day. We have customers from minimum from 0 to 7,388 customers. Whether or not it's open, that's 1, 0, and 1, because that's a binary feature. We have, let's just skip ahead a little bit. So the day, month, year, these are the extracted features. So these go from the day goes from 1 to 31, makes sense, days of a month, 1 to 12, 1 to 12 months in a year. The year goes from 2013 to 2013 to 2015. The day of the year goes from 1 to 365. The week, 1 to 52. And whether or not it's a weekend, 0 to 1. Okay, so now, although this isn't specific to Wrangling, they are important for some Wrangling steps that we'll take later. So we visualized some of the features. So, and also because we discussed group by later, earlier, so this is it in action. So with pandas group by, this allows us to see a certain variable in relation to another one. So what we see here is we group all the observations by day, right? So we have the day, and this is because we wish to view, because this tells us pretty much, oh, if we're looking at days, is there any pattern? Is there any sales pattern in days? So these are the days between 0 and 31. We see that there does seem to be, it does appear that there is more sales at the beginning of a month compared to towards the end. Now notice that this takes every day in the month and looks at it on average over the 2 years. So all the first of every month they are all added together by this sum. So this takes the first of every month, adds everything together. And that's how we have this plot. Someone's asking a question. Okay, so yeah, so the group by allows us to group all the days together. So all the days are grouped between 1 to 30, depending on the day of that particular sale. Then we sum them all together. Now notice this doesn't have to be summed. This could have been mean, median, depending on your use case. But in this case, we wish to see how sales varies across the month. That's why we're using month. To explain this reset index, I'll need to show you what we see without using it. So if we just did this. Oh yeah, sorry. I forgot that I need to run this. I need to see that. Okay, so this just returns where we have this index, the day as the index and the raw value. However, to be able to, because I'm using ggplot to plot this, and to plot this, I need to feed it the columns representing the day and the sales. So reset index, so what reset index does is that it moves the index into a column. So rather than being the index, because this is technically a 1-column data frame, right? It just has sales. The day from 1 to 31 is just in the index. But when I add reset index to this, it makes it into a 2-column database where there's now day and sales. So, so we see this. So we can also look at it by month. So all the months, the sales are grouped by the month and then summed together again. Now it does appear that there is more sales at the beginning of the year compared to towards the end. So we can also look at the day of week. Also look at the day of week. So we do the same thing. We group by day of week, we sum it, we reset the index, and it does appear that there is more. there does appear to be more sales at the beginning of the week compared to, I mean, as a matter of fact, it looks like it drops at exactly the weekend for 6 and 7. Now we have 3 years worth of data, 2013 to 2015. We can also view that to see if it varies. It does seem that there's been a sharp drop in sales for 2015 compared to 2013 and 14. As a matter of fact, it seems to be a trend from 2013. Okay, so now that we visualize this, we can start to, okay, so another thing to look at is that we noticed when we look at the information ahead that we had some sales of 0. Now, this is an interesting thing to look at. Why would there be a sales of 0? Was the shop not open? Because we also have a feature that tells us whether or not the store was open on the day. So now we can look at, so if we look at the shape of the data when the sales is 0, we see 172,871. When we look at the shape when the stores are open, we see just a little bit less, just 54 less. So now, looking at this, most of the times when the sales was 0, it is because the store wasn't open, which makes sense. A store can't sell anything if it's not open. But there are, however, 54 observations where the store was open, so where store.open is not 0, and also where sales is 0. Now, the reason I included these 3 parts is because we looked at indexing earlier, right? We looked at where we index the data frame based on multiple conditions. So this is us indexing the rows. This is us subsetting the rows, rather subset is what I meant. Subsetting the rows based on the observations where the store is open, is not open, but the sales are 0. In this, we have 54 observations where the store was open and there's a sale of 0. Now, this might be a mistake or might be an error in recording, but I mean, or maybe it's a day they were open and they decided not to sell. Or maybe no one came in to buy. Now, okay, so now let's just have a quick look at those observations. So we have sales of 0, but open is 1. Okay, so we can also check missing. So we also checked earlier, we saw that there are a bunch of observations with null values, right? So with this, okay, yeah, so this is subsetting the data based on what we looked at earlier, where like we don't want observation. So this is a tilde, that is a negation. So we don't want a situation where the store is open. We don't want observations where the store is open and the sale is 0. Because I mean, those don't seem right. They seem like they should just simply be dropped. And also because we have no other information to let us know what could be bringing about a situation where the store isn't open, where the store is open and they have no sales. So those were dropped outright. Competition distance was one of the features we looked at earlier. We saw the competition distance. Yeah, so competition distance, now let's look at this one, it's better. So competition distance has, this one. Yeah, it only has 2,642 null values. That's not a lot. That's, I mean, we could either simply drop them or we can just, oh yeah, so that brings us to the topic of how to handle, some ways to handle outliers. So, some ways to handle NAND, missing values, rather. So with missing values, there's the pandas method, fill NA. So this lets us decide on a number of ways to fill NaN values, right? So here we're just simply asking it to just replace it with the median of the values that do exist. Now, because it was just about 2,000 values, we could have dropped them. Ideally, what I would usually do in like if I'm taking part in if I'm looking at a problem such as this, I look at other ways to deal with it before dropping it. Dropping it, sometimes it's easier to just sort of move on, but there are other ways to deal with it. We can try to understand why that is, why they are NaN. It's possible that they are NaN because nothing was recorded for them. So maybe 0 would be appropriate for that, right? Or it could be that we can just fill it with the value that is most common. that is also possible. But here we're just taking the median because this is a numeric value. We're just taking the median and just replacing it with that. So competition distance has been sorted. So yeah, so we have a few more visualizations where we look at a few more features like store type and an assortment. So the reason I included this is one of the ways, like one of the things you come across when you're trying to wrangle data is you come across features like categorical features, as we discussed earlier. So store, if you remember, store type was store type included categories that A, B, C, and D. So, but before we do any of that, we need to just have a quick look at it. So again, we are grouping by store type, and we're looking at the sales and summing them together. We see that the store type A appears to be way ahead of everybody else. But why is store type A dominating the sales? Is it because there are more types of one possible reason for that is because there are a lot more stores of type A than type B. So to confirm that, we can also make a plot that counts them, that value counts them. And we see that these are both very similar. So store type A only simply dominates the sales because there are many types of store type A. So yeah, so the one way of dealing with categorical variables such as this is by applying one-hot encoding. So one-hot encoding is where we convert categorical features such as this into a form. So this actually requires some discussion before we move on. So with a lot of the features that we've seen, right, they are all numeric. A lot of them these are open one, promo one, and these are all ready to be fed into a model. Then we have like store type assortment that are A, B, and C. These are letters, these are categories. We can't feed this into, well, we can't feed them into a machine learning model. So now, one easy way to deal with this is just simply to convert these values into numerical. Say A is now 0, say B is now 1, C is 2, and D is 3, and just move on. And there are sometimes when you do this, and it does work, it works well enough for what you need. But there's a problem with that method. So when you take the store type, let's say store type A, and you change its value to 0, and then the store type B, and you change its value to 1. So does anyone have any questions? Okay, and then there's store type C, and we say that as a value of 2, right? When you do something like this, you are unwittingly, and you feed this into a machine learning model, you're telling the model that there is a certain relationship between store type A and B. So you're telling it that store type B is 1 greater than A, and store type C is also greater than B by that same measure. So you are applying a meaning that might not exist in real life, that actually does not exist in real life. There is no reason for us to think that. So now let's say that we have store type D, or let's say E now, for example, and store type E is 4. Now you're now literally saying that there is something about store type E that is 2 times greater than store type C, because this is a 4 and this is a 2, right? And you're saying that there's something about store type E that is plus 4 of store type A. So this would not be, now there are situations where this might work. Like let's say, for example, that you're working with like a ranking, like we're looking at the number of stars that a restaurant has, whether it's star A, B, C, or D. Now, if you do something like this, this might work. Now, there's still some problem with that, but it might work because there is an order to ranking, right? Let's say you're saying, let's say you're saying 5 stars, or 5 stars is greater than 4 stars. Now, the problem with that sort of situation is that 5 stars might not be exactly numerically 1 greater than 4 than 3, because these are subjective. People give those stars. However, it still works better than in this case, where you are assigning it to a store type. So what we do in this situation instead is that rather than just have this as a column where you just have 0, 1, and all of these numbers, you one-hot encode them. So rather than that, we'll now have 4 columns instead. So for store type A, the first value here will be a 1. For store type B, this is a 1. So we are now adding 4 additional columns to represent these store types. So this is better because we are saying, oh, like this first column represents store type A. So an observation that has a 1 here means it's a store type A. The other observations that are not store type A, they have a 0, so they are not store type A. For this second column, we're saying, oh, this second observation, it's a store type of B because it has a 1, the others don't. So that is what we do here when we apply. So to do this, we use dummies. Pandas has a get dummies feature. We feed it the store type. We are adding a prefix here because we want it to add store type before the A, B, and C. So now we have this one column now has been converted into 4 columns, which is a 1. Sure, okay. So yeah, so this has been one not encoded. Just before I move on, someone's asking about this. I won't spend too long on this because it doesn't really fall under the data wrangling, but this is just for me, like as you know, there are many visualization libraries for Python. There's matplotlib, there's cbun, and a few of those. ggplot is just my personal favorite because I used it when I used the R, and I just sort of kept using it on Python. So someone's asking about geombar, and labs. So yeah, so to make use of ggplot, this second part is where you specify the type of plot you're making. So this is a geombar because I'm making a bar plot. The labs just refers to the label. So I'm telling it for the X label, give it store type, and Y axis rather. For the X axis, give it a label of store type. For the Y axis, give it a label of count. That's all that is. Okay, so back to one-hot encoding. So yeah, so now we have 4 different features for store type. Later on, we'll be making use of concatenate, as we looked at earlier, to sort of add these 4 columns back into the main data set, because this is not the main data set, right? Train store df is the main data set. So we'll need to add these 4 columns back in there. But before we do that, we'll do the same thing for assortment. Assortment is also, sorry, we have more questions. Thank you. So assortment is also another categorical feature or column. We also have a look at this real quickly. There are 3 types of assortments, A, B, and C. B appears to be really, really like small compared to these 2. Again, we look at the count and we see that this is explained by there just being multiple, there just being more stores of assortment types A and C, more than type. Again, we do a dummy variable for assortment. So now we have the 3 columns, A, B, and C. Now there's something that I should mention actually before we move on. I didn't use it, but it's something that should be mentioned for dummies. There is a parameter that could be stated for dummy, which is, I believe it's drop first, if I'm not wrong. Drop first, exactly, okay, drop first. So now if we specify drop first, right, and we say true, what it does is it drops the first column. So take for assortment where we have assortment A, B, and C, it drops assortment A, and there are now only 2 columns. In the case of the store type dummy where we have 4 store types, it drops a store type A as well, and we only have 3. So why is that important? Why is it dropping them? So remember that as explained here, we are saying that, okay, we used to have 3 rows, right? One was store type A, B, and C. But now we have this one-hot encoded where each row still represents the store type of the observation. However, we're now using 4 columns to represent that, right? However, if I was to drop this, let's say I were to drop the first column, which is what I'm doing right now. So how do we know which store is store type A? Well, we know this is store type A because all 3 of these have zeros. If all three of these have zeros, then that means it's store type A. If one of these has a value in there, like all these three do, then they are not store type A, they are store type A, B, and C. So it's actually more efficient because at the end of the day, you don't want to have too many dimensions, right? If you can avoid it. So this would actually work just as well as before when we had the 4 columns. So we can always drop the first because the absence in the 3 remaining columns also means that this is true. So that is, so that's something to consider. So drop first. I would personally, when I use this, I always drop the first because the first is redundant. You don't need it. The model doesn't need it. It can function well without it. So if you have more questions, drop the main column to avoid repetition. Okay. Someone saying that we dropped the, sorry, are you referring to the one hot end like this, the first column, right? So, okay, let's move on. You can unmute your mic and pop in at any time. Okay, so yeah, so we did the dummies for assortment as well. This is the one hot encoded columns for assortment. So okay, state holiday as well also has categorical features. So the reason I did this, so I'm using map here. So we haven't really talked about map. Map is a way to sort of, okay, so the reason why map was used there is this. For the state holiday, let's look at state holiday. So when we look at state holiday, so value counts is a way to see, it just gives you a table, right? A count of all the values you have in your feature. So for state holiday, we have these values. We have 0, A, B, and C. But for whatever reason, so not for whatever reason, actually, I know why. So this is 0. This is 0 as a number, and this is 0 as a letter. So these are being seen as two different values, so they are counted separately. So I'm using map to sort of map both of them into letter. So I'm telling it here. So this is just saying map was called on state holiday, and we are just giving it a mapping dictionary saying if a value has a number 0, map it to letter 0. Then these ones are A is A, B is B, C is C. These ones don't really matter. Now, if a value is a letter 0, because we know this is a letter because it has the quote around it. If this is a letter 0, then map it also to a letter 0. So what that does is pretty much it combines these two categories into one. So we had to do that before one-hot encoding, because had we not done that, we would have had 2 columns here. We would have had 2 holiday 0 columns because we have 2 categories of zeros. So I actually find that it's easier to understand what things do when you actually use it for something specific. So I don't really have to go into map and go into much detail because we see that it's really mapping from one value to another. So where is another situation where this might have been useful? So imagine that I had a column for gender, right? I have a column for gender and the values are male and female. Now, because this is male and because these are only 2 categories, I don't need to one-hot encode this, right? I really could just change them to 0 and 1. Now, 0 and 1 is okay in this case because now what I'm saying makes sense. I'm just saying that the value of male and 0 means like I'm saying that for the column of male, 0 means 1 means female and 0 means not. Sorry, 1 means male and 0 means not male. So I'm changing this. Okay, So now in this case, we don't have to use one-hot encoding. We can just map the values of male and female to 1 and 0. So to do that, we would just simply be doing this, right? We'll just simply be doing dot map, and we would say map dot male to 0 and dot female to 1. So this way we don't, so in a case where we had a gender column, we could have just easily mapped it to 0 and 1 without necessarily having to call one-hot encoding. Okay. So again, we one-hot encode, now we one-hot encode the state holiday variables, and we have this holiday 0, A, B, and C. Now, if you look at the documentation, it tells us exactly what that means. So holiday means state holiday, indicates a state holiday, blah, blah, blah. So 0 is none, A, public holiday, Easter holiday, and Christmas. Okay, so now we have all these dummy variables, right? We've made 3 dummy variables. Now we can use Panda's concatenate method to join them together. So we are joining the main data sets, which we always had. We are now joining the store type, the assortment, and the state holiday variable, and we are joining all of them in axis 1, meaning we are stacking them side by side. So we are adding those as extra columns, and we can see that here. So this is all of them now joined together. This was the normal data set, and the assortment types and the holidays have now been added to the right. Now, one thing that we should not forget to do is, oh yeah, so we also engineered 2 features here. So this is, so remember we have 2 columns for competition and pro. So a competition tells us, this says that the competition tells us the distance to the nearest competitor store. It also gives us the year and the month of the competitor. So this is a way for us to see for how long the competitor has been open. So because remember, we are getting the year and we're getting the year and the month separately. So we need to calculate the distance between the year, the current year of the data we're looking at, and the competition open year, but also compare the current month and the competition month. And we use this to sort of get how long ago the competition was open. The same with the promotion, how long has been a promotion been ongoing? We do the same calculation here. So here we drop all of the features. So because we've one-hot encoded store type and assortment and state holiday, we don't need them anymore. We are dropping this promo interval because they are the ones that add like 50% null values. They are not, we can't like drop half of the data set, but we also don't want to fill in missing, but we also don't want to fill in median or whatever into these. So it's just best to just drop the column itself. We don't need dates because we've already extracted day and week and all the numerical features from date, so we can drop that as well. So yeah, so here is where we drop all of the features we no longer need. Now for the remaining ones, we just fill in wherever there's still a null, we fill in a value of 0. Now at this point, because of everything we've already done, the values of 0 is only filling in these 2 features that we just engineered. So here we're just saying where it's null, which usually represents that the competition does not exist. So we're just saying 0 because we're saying 0 since the time where there was a competition. So 0 makes sense here. So this is the final data set. They're all numeric. And I'd say at this point, we are ready to we're ready to pass this into a machine learning model. At this point, we just simply chose, now a standard scaler was used there to sort of scale the data, but because for XG, so we're using XGBoost, which is a common model used in data science competition. At this point, we're actually out of the wrangling part, but it was just we just had to come here just to show that. But there is still some wrangling going on when we wrangle the test data set, exactly like we did the training data. So we'll come to that after getting through the modeling. So XGBoost is a very popular model with competition, so that's what we're using. So XGBoost, like most decision tree based models, doesn't really require scaling the data. We don't need to scale all the values to between 0 and 1 or between -1 and 1, but it's just a nice, it's just something that I've gotten used to, so I'm scaling the data. If anyone's not familiar with scaling, to speak up, but ideally, so many machine learning models, right? If you have a lot of features like this, let's say one feature is between the range of, let's say one feature is a population feature and it measures the population of a country. And that obviously, let's say is between 0 and 50 million. But then you also have another feature, which is like year, right? And year is between, let's say 1960 and 2020. There is a disparity between the ranges of two of those features. One is in the millions and the other is just between 2015 and 2020. A lot of machine learning models do not work properly when they are such different ranges. You don't get the full accuracy, because the feature that has the one in the millions will dominate the small one. So one way to do that is to typically scale the model, scale the features. Like let's say we scale everything between the values of 0 and 1. However, decision tree based models, because they are non-parametric, they are more robust to scaling, to unscaled data. They handle that better. They don't need it because decision trees are like if-else based sort of calculations. So it doesn't really care whether or not you scale it. That is why I said that scaling isn't necessarily, it's not necessary for using XGBoost, but I like to do it anyway. So yeah, so here this is the full data set. This is everything we need. However, sales is what we are trying to predict, right? So what I'm doing here is, train df.columns.values. This gives us all of the columns, but I'm asking it to remove sales from there because sales is the target we're trying to predict. It shouldn't be in the features that we're using to predict. So this now gives us a list that is just all of the column names without sales in there. Okay, so here we split our training sets, 80-20, 80 for the training, 20 for the test set. When we split it, we use the features to subset. So we're saying go into train df and only pick up the columns that we specified in features. So pick up everything except sales. Then for the Y, for the target, we're using sales. So now we have our X train, X test, everything. We're scaling it down. This is getting into the XGBoost matrix or array format. Now to get a really good result out of this, you can do this when you're playing with it. This needs to be at least 20,000 rounds for you to get a really good, but it takes such a long time because remember, we have over 1 million observations. I set this to 250 just so you can train much quicker. Now I'm using RMSE, but in this competition, it was required to use our Rms Pe, which is, but I didn't want to implement that. And also because it's not necessary to the wrangling. So I'm using RMSE. However, after training, you can still use this to sort of to evaluate your model and see how it's doing. And you can compare that to the leaderboard. So normally with competitions like this, after you've trained your model, you now have a train model and everything, you're also given a test set. So the test set is supposed to be the one you're submitting, right? So now it means that all the pre-processing, all the steps we took with the training data, we need to do it on the test as well. So that's what this part is for. Now, ideally, it would have made sense to just create a function and put everything in there rather than writing this again. However, I wrote it out so it's clearer and so that we can see the steps that we took in training replicated for the test. So here we go through the same step. We merged the test set with the store data frame. We converted the dates to date time. We extracted all these useful features, but this time we're doing it on the test data set. We also get the dummy variables for the store type assortment. we concatenate them together. We also engineer these two features. We fill everything that is left with 0. Now, when I ran this the first time, holiday B and C were not present in the test set. So that means that there is no data in the test set where there were holidays B and C. So that means we can just now, because a model, you need to feed it the exact same features that you fed it in training as in test. So for that reason, we just have to create those columns and just set them to 0, saying they're not present. So that's okay. Now we run a prediction on all the test sets, we get the result. This allows us to read CSV. This allows us to, oh yeah, sorry. So this is a sample submission that was given by Kaggle to let us see what the sample submission should look like. So in the sample submission, they said, so they specified that they want it to look like this, where there's just the ID of the observation and the sales for that day. So based on that, we do that, we create that. We use the pd.data frame to create a data frame where we specify the ID is gonna be the ID of the observations in the test data frame, and the sales is gonna be the predictions we just made here. And with this, we can, sorry, this is submission.csv. So with this, we can dump a CSV file to look the way it's wanted in our submission. So this could just yeah, that's the end of the workshop. If you have any questions, please, I'm a liaison. Obviously, we do have some questions in the chat. Creations, I think we drop them on the search column before you introduce the dummies. Oh yeah. So yeah, we do drop them. We drop those main columns. We drop them much later. Someone said, what is Rms Pe? Yeah, so the difference between Rms Pe and Rmse is the P. So the P refers to percentage. So I can just show you real quickly. I think I have the formula. So normally in root mean squared error, so root mean squared error is just, so error refers to the residual, right? So the difference between the actual value and the predicted value. So let's call it y hat. So that's the error. Then the root mean squared error. So the squared root mean squared. So the squared means we square that, right? Then the mean, we take the mean. And then the roots, we take the square root. Now for Rms Pe, we add this. The only difference is this, we divide by yi. So we scale it by the actual predicted value. So if you take out this yi, then you'd have root mean squared error. Now this was the metric that was specified by the people that hosted the competition that they wanted. You'll be able to use a pipeline and that's automatic the wrangling, or is it just for model evaluation? So yes, there are some pipelines that can be used to automate some wranglings. So the one hot encoding, for example, could be automated. That could be added to the pipeline. There are certain ones. Okay, let's go through the process and we'll see which ones. So let's use the test, for example. Okay, so yeah, the field NA could be added to the pipeline. So let's say this, for example, so see where we checked whether it's greater than 6 or it's greater than 5, meaning it's a weekend. We can't add this to the pipeline. However, we could add the fill in the NA to the pipeline. The one-hot encoding, though not get dummies. I believe there's a sklen. Let's check that real quickly. So sklen one hot encoding. So there's a sklen function that's a one hot encoded. The pipeline is made by sklen, so they are allowed to do this. So that would be so different. The dummies we're using right now is from pandas. So So yeah, this is from Panda. So we can't use this, but we can use the skLens one-hot encoding. That can be added to the pipeline. So yes, so there are certain wrangling steps that can be automated, and there are those that can be automated. So the random state. Okay, someone's asking, why do we always set the random state on the model to 42? What would happen if we set a base? Oh yeah, so random states. This is just to make things reproducible, right? You set it to a number. So that way, when you, let's say, for example, when you split the data, if you use the exact same number, it keeps the splitting the same. It allows to be able to compare, performance or results of a model. Now, why is it being set to 42? So if you don't know, I'm actually really happy to answer this question. One of the most popular sci-fi books ever made was The Hitchhiker's Guide to the Galaxy. And one of the very popular things from that book, which I'm a huge fan of, the author died a long time ago, part of what made him into a legend, but the books itself are legendary. So there was a part in that where human beings, apparently in the future, they built this super intelligent AI. It took them, I think, hundreds of years or thousands of years to build. So sorry, it took them millions of years to. They built a machine, an intelligent machine, and it took it a million years to sort of answer all the important questions to life, right? So the answer to the life, to universe, and everything. So at the end of the millions of years, the machine came up with an answer and said it's 42. So that is why 42 is a very common chosen number, especially within AI and everything. So yeah, so it doesn't have to be 42. You can put in whatever you like, but it's just convention to use 42 because 42 is the answer to all the important questions in life. Cool. Does anyone have any more questions? Cool. So yeah, that's it for this workshop. Nice to meet you guys, and hope to see you again. Take care. Bye.
Bye-bye.